let's talk about this first. Is there any problem that a computer cannot solve?
Yes.
Which was you're saying yes, there is a problem that the computer cannot solve. So a big part of after inventing this modern day programmable computer, quote unquote, well, the question was very simple. Let me back it up actually a little bit. Let me back it up. In I'm missing the exact year, but some time ago, David Hilbert, very, very, very famous guy. He basically invented everything. Like everything of modern day mathematics was him. He was the king, the god of mathematics, basically. And he had these set of problems where he was trying to see if mathematics was a perfect model of the world. And he had a few problems here and there, and he's like, oh, if this is true, then mathematics. If this is true, if this is true. So he had these 3-4 problems, right? I believe it was 3 problems. And I believe like 1 or 2 were solved, 1 or 2 were disproved by a student, by Gödel. A lot of people may recognize that name. But I don't want to talk about that. I want to talk about the decision problem that Hilbert posed. One of these fundamental questions about mathematics was very simple, or not very simple, but this was the question. Can we know, or can we determine, if every statement can be proven or disproven? So, basically, what that easier way to say it is, given enough time, will we be able to determine if a given statement is true or false? Or not true or false, is provable or disprovable. That's the idea behind the decision problem. Alan Turing comes in the picture. He's like, I'm going to change up this wording a little bit to satisfy my definition of a computer. So he says, is there any program that can determine if said program will halt or not halt? Now, for those of you maybe not familiar with a lot of computer, what does that mean? So you know when you write a piece of code, while true, execute something, and it just executes forever, is an infinite loop? That piece of code will not halt. That means that piece of code will go on forever and ever and ever and ever and will simply not loop. And something like this, and the question was, well, if you give this to a Turing, if you give this to a Turing machine, it'll just continue to do something over and over and over and over again. It's not halting. Now, a program will halt. Obviously, the contrary example to this will be if the program actually does end up stopping. So that's your idea of halting and not halting. And Alan Turing had converted the decision problem. Now, he's also a mathematician, so don't only think that he's just doing this theoretically. This is very deeply integrated in mathematics. It's just that I'm going to be skipping out a lot of that just to get to the understanding of what exactly he did.
But
right?
Hold on, how are those two statements equivalent?
Okay, so Hilbert asks again, can we know if a statement can be proved or disproved? And Turing asks, can we know if a program will stop? That means it has been executed. That means it was successful, quote, proved, or not stopped. Cannot be proved. Get it? So that's basically the idea behind converting that to now what is known as the halting problem. And this is a very, very, very famous problem that'll let almost every single first or second year or any year's computer science student will be aware of, right? Or at least knows a little bit about. And this is how he phrases the problem. And this was his solution to the problem. Now, this is a little confusing, so bear with me. This is crazy, okay? This is going to be insane. So just everyone listening, everyone viewing, just chill. The halting problem. This was Alan Turing's answer to the decision problem. And he basically said, can every statement be proven? Or do we know if this can be true? And the answer is no. We don't know. And this is, right? Yeah, exactly. We don't know. And this was his explanation. Take a program that can do two things. Think of it like a function. It takes in a program and then it does something. Now, what it does is two things. Step one, it will check if the program halts or does not halt. So obviously for this, we assume that we can make a program that will determine if a given program would halt or not halt. So we are assuming the statement to be true. Valid? Valid, right? So we're assuming that this kind of machine can be made, and then we're going to take it from there. So let's say we can make such a program. So the first thing this program will do, it has two things it'll do. The first thing it'll do is check if the given program will halt or not halt. Very, very straightforward. Then, if the program will halt, it will spit out yes. And if it will not halt, it will spit out no. Now, here's the thing. The second thing it does is a little confusing. So again, just bear with my logic here. If the program halts, that means it stops, and it says yes, the second part of this program will loop infinitely. That means it will not halt. But if the given program does halt, sorry. If the given program does not halt, that means the given program will loop infinitely. The secondary program will halt. So here's the program once again. Let me make sure this makes sense. It takes in a program. If that will loop infinitely, the second part of this program will stop. But if this program will not loop infinitely, the second part of this program will loop infinitely. And that's basically this whole program. Now, Turing said this. What if we put this whole program into itself? Follow the logic. Follow the logic.
Oh.
The program, let's say, does not halt. Right? That means it goes on infinitely. Right? It does not halt. Then the next part of the program will stop immediately. But then if it stops, that means it did halt. So this should go on infinitely. But if it goes on infinitely, then this should not halt. Then this should stop.
So wait, hold on.
Does that make sense?
Is he gonna like infinitely feed the program into itself?
The conclusion is that this is inherently a mathematical paradox. That you cannot make a program that can determine if said program will halt or not halt. Basically concluding that the decision problem was solved and is untrue.
But wait, hold on. Why can't
ask your questions?
Okay. Why can't you just say that the program that determines if a program will halt or not halt?
Yeah.
There's only one part to it, and it either says yes or no, and then there you go. There's your program.
No, but you're trying to prove that statement, man. Come on. You're trying to prove if that statement is true. You're assuming that there is a program that exists like that, and you're trying to see, well, would that work? So what he did is he created a counterexample. He put the second instrument right next to it, right? And do the exact opposite of what this guy does, basically.
Yeah.
And then send that whole thing into itself.
I get it.
Right? So it's crazy. And this is basically how he answered the halting problem and the decision problem, which was one of his greatest feats. And again, it was massive because basically it proves that a computer cannot find the answer to every question. And that's a little scary if you think about it.
But hold on, I have another question for you.
Go for it.
If you assume that it's true, here's the problem. Okay, so the statement you're trying to prove is a there exists statement, right? Because you're trying to find one program that can determine, right?
Well, no. The statement is every. The statement is every program has a provable or disprovable solution.